Srinivasa Ramanujan was a largely self-taught genius who emerged from an orthodox Hindu family to become one of the most influential mathematicians of the 20th century. Although he had almost no formal mathematical training, his remarkable intuition led him to make extraordinary contributions to several areas of mathematics, including, in particular, number theory. His work, grounded in the very ethos of the soil, much like this banyan tree, developed an enigmatic foliage that led others to sprout new roots and enlarge the canopy of contemporary mathematics. Ramanujan's mathematical explorations were abruptly cut short by his untimely death at the young age of 32. Now, almost 100 years later, we look at his life, his work, the legacy he left behind, and also meet some of the mathematicians influenced by his work, both here in India as well as around the world.
Srinivasa Ramanujan was born on the 22nd of December, 1887, in a small district town of southern India. To commemorate his birth centenary, we made a docudrama film with enactments in 1987, more than 25 years ago. Today, walking in the footsteps of the genius, we visited many places associated with his life with a group of mathematicians: Ken Ono, A. Raghuram, K. Srinivasa Rao, and T.V. Venkateshwaran.
It's in this small town of Erode that Srinivasa Ramanujan was born.
Little Ramanujan grew up in the temple town of Kumbakonam, located on the banks of river Kaveri. During his childhood, Thennai village primary schools dotted the rural landscape of Tamil-speaking areas. Collective recitations set to metrical verses help children develop a keen mnemonic ability. This oral tradition might have encouraged little Ramanujan's flair for logical thinking and deep reflection.
In the Thinnai schools, the unique function of the pedagogy is to cultivate a memory which scholars would call it recollective memory, which is you remember and you memorize in order to be able to recollect. Here, writing is only an aid to memory, and the particular ways in which the memory was trained was in terms of, like you take the particular case of the Ponnilakam, the learning of the numbers. So there is a head monitor who recites the number, and then the student is supposed to recite it after him, and while reciting, which is to vocalize what he hears, and then there is a heap of sand in front of him, and then he draws the graphic symbol of the number, which is the number notation, and recites loudly, so that you have the qualities of vocalization and visualization and memorization happening at the single continuum. Particularly what recollective memory trains you is to strong visual sense of the numbers in relation to each other. So the Kangayam primary school that he went to, we know for sure that the Thinnai schools continue to exist till about the 1920s. This familiar world of creating and cultivating an intimacy with the world of numbers was definitely part of the orientation of the Thinnai schools.
Sir, if 0 is divided by 0, can that access to everyone?
No, there are always exceptions. Ask Ramanujan. He was India's last great mathematician. He said the answer.
It was in this town high school of Kumbakonam that the magical world of numbers, trigonometry and geometry opened up for the ever-curious little Ramanujan.
That was an intelligent question you asked. You like sums, don't you?
Yes. You know, sir, I want to learn lots. I want to find out what the highest truth in mathematics is.
What? What did you say?
What the highest truth in mathematics is.
What we learned from the early mathematical development of Ramanujan is the importance of problem solving at the primary school level. The Hungarian mathematician and educator George Polya observed that mathematics develops critical thinking and a love for expressing ideas precisely. In my own experience, early exposure to the beauty of abstract mathematical reasoning and access to math and puzzle books helped me develop a passion for mathematics.
At the age of 12, Ramanujan borrowed from older students Loney's textbook of plane trigonometry and completely mastered its contents. This book went far beyond standard curriculum and introduced rudiments of calculus too. But the book that really transformed Ramanujan's life is Carr's synopsis of elementary results in pure mathematics, borrowed from the local college library. He engrossed himself in its methods of analysis and demonstrations and proved the propositions and formulae contained therein all by himself.
On magic squares and things of that kind.
In 1904, at the age of 16, based on his outstanding performance in school, Ramanujan won a scholarship to the government college in Kumbakonam. By this time, he had already started producing original research. With not much encouragement from his professors and in isolation from the mathematical community of his time, he worked on problems in algebra, trigonometry and calculus, studied infinite series and played with prime numbers. A raw genius, he independently rediscovered several existing results as well as made new discoveries. He is said to have drawn inspiration from his family deity, the goddess Lakshmi Namagiri. However, being totally immersed in mathematics, he neglected all other subjects, and the government college did not renew his scholarship. So in 1906, he moved to Patayappa College in Madras, but there too he concentrated exclusively on mathematics and did not pass the necessary examinations to enter the University of Madras. From the age of 14, Ramanujan wrote down his mathematical findings in 3 notebooks, which have become famous now as Ramanujan's Freight notebooks. These notebooks contain a treasure of over 4,000 theorems, corollaries, and other results. Proofs form the backbone of modern mathematics. But Ramanujan, inspired by Carr's book, had developed a highly unconventional style of working by finding patterns in numbers and formulae and relying on intuition and induction rather than on proof and deduction.
An intense Ramanujan, constantly toiling with equations, struck a rich purple patch with hypergeometric series, elliptic functions, Q series, continued fractions, consuming all his youthful energies. This productive period was briefly interrupted in 1909 when, as per the prevailing customs, Ramanujan's parents arranged his marriage to Janaki, a girl barely 9 years old. Soon, household responsibilities compelled him to leave Kumbakonam and look for a steady job in Madras, the colonial center of British administration. For some time he tutored students in arithmetic and somehow eked out a frugal livelihood. Finally, he got a clerical job, largely due to the chairman Sir Francis Spring of the Madras Port Trust getting thoroughly convinced of Ramanujan's mathematical ingenuity.
There was a community of people in India who sort of also supported Ramanujan during his initial years. One is people like, for example, Mudaliar, who was his teacher in the Pachapa college. You know, I mean, even after Ramanujan had to leave the college and for unemployed for quite some time, I mean, Hardy's books were introduced by Mudaliar to Ramanujan. The second is collector, Ramchandra Rao, who paid him from his own personal salary a small amount as a stipend so that Ramanujan can work on maths while he was no longer a student. Third is people like Narayana Iyer, who got him a job in the port trust, who sort of entertained him every day in his house so that they can discuss maths. And he continued to help Ramanujan even after Ramanujan went to Cambridge. People like Professor Ramasamy. Actually, he was a government servant. He was one of the founders of Indian Mathematical Society. People like him encouraged Ramanujan to write. I mean, till then Ramanujan was sort of keeping a journal, his notebooks. I mean, he was just keeping it to himself, maybe showing to a few people. They said, no, that's not the way, for example, science is done in modern world. So they encouraged him to publish. So some of his earlier papers came in Indian Journal for Mathematical Society. His work on probabilistic number theory or elliptical function or continued fractions, they all have a lot of application even today. It's an important contribution.
In 1957, the Tata Institute of Fundamental Research in Mumbai brought out a facsimile edition of Ramanujan's notebooks, which had hitherto been lying dormant at the University of Madras. For the first time, Ramanujan's startling results were brought to the attention of mathematicians around the world. Subsequently, in 2012, the Tata Institute published a second collector's edition of Ramanujan's notebooks. Mathematicians are remembered not only for their theorems, but also for their insightful conjectures or intelligent guesses they believe to be true. One example is Bertrand's postulate. The French mathematician Joseph Bertrand will forever be remembered for the conjecture he made in 1845 when he was just 23. Bertrand observed that between the number 3 and 6 there is a prime number, 5. Similarly, between the number 10 and its double 20, there are 4 primes, 11, 13, 17 and 19. Generalizing this observation, Bertrand postulated that between every number n and its double 2n, there is at least one prime number. And Bertrand checked that his postulate was true for all numbers less than 3 million. However, this still does not constitute a proof. For example, it does not show that there is a prime between 5 trillion and 10 trillion. It was the Russian mathematician Pafnuty Chebyshev who 5 years later gained immortality by proving this result, and the postulate was promoted to the status of a theorem. However, Chebyshev's proof of the result was long and complicated. In 1919, Ramanujan provided an elegant 2-page proof of this theorem in an article that appeared in the Journal of the Indian Mathematical Society. His proof gave rise to the notion of what are now called Ramanujan primes. Interestingly, 13 years later, unaware of Ramanujan's proof, the Hungarian mathematician Paul Erdős, then just 18, gave another proof. This proof, although similar to Ramanujan's, contained a new idea that allowed Erdős to generalize Bertrand's postulate in an entirely new way. Just as Bertrand's postulate inspired many mathematicians, including Ramanujan, Ramanujan's conjectures have in turn inspired other mathematicians to enlarge the edifice of mathematics brick by brick.
I beg to introduce myself as a clerk in the Madras Port Trust. I am now about 25 years of age and striking out a new path for myself. I have made a special investigation of divergent series. The results are termed by the local mathematicians as startling. but they are not able to understand me in my higher flights. If you are convinced that there is anything of value, I would like to have my theorems published. To Professor G.H. Hardy, Trinity College.
These theorems of his must be true, because no one would have the imagination to invent them. He must be a mathematician of the very highest order.
Ramanujan's letter to Hardy, dated 16th January 1913, is one of the most famous letters in the history of mathematics. It marks the first recognition outside India of Ramanujan's remarkable talent. In the late 1920s, after Ramanujan's death, this letter and a subsequent one he wrote to Hardy spawned numerous papers by several mathematicians.
It is here, at the Trinity College, that Professors G.H. Hardy and to a lesser extent J.E. Littlewood mentored Ramanujan, only to be continually amazed by his remarkable originality. Later generations of mathematicians were to proclaim his conjectures as unexpected, elegant and deep. But the most remarkable aspect of Ramanujan's encounter with the West was that, for the first time and in his own right, he could pursue the professional career of a creative mathematician.
When he arrived in England, he collaborated with Hardy, and they developed the famous paper on the partition function, which was an asymptotic formula. But as Atle Selberg points out in his, his centenary lecture on Ramanujan that was delivered here at the Tata Institute in 1987, he says that if you look at Ramanujan's letter and see the first term that he had written, that coincides with the first term of Rademacher's formula, which was discovered in the 1930s. Rademacher discovered an explicit formula for the partition function, whereas Hardy and Ramanujan discovered only an asymptotic formula. Now Selberg, I think, semi-humorously points out that Hardy was to blame for this debacle because Ramanujan was going in the right direction of trying to get an exact formula, and it was Hardy, he says, who steered him in the wrong, if you want to say, wrong direction.
Very interesting. D upon dn, n minus 1 upon 24, he's right. But what's made him so certain? The function has so many forms. To have chosen the right one is nothing less than an extraordinary stroke of genius.
The First World War saw Cambridge University almost bereft of students. But the wonderful collaboration of Messrs. Ramanujan and Hardy during that time stands highlighted for its seminal contribution to the number theory. Our Indian research student wrote over 30 papers, 7 of them jointly with Professor Hardy, and ultimately he was delighted to be finally bestowed with the University of Cambridge degree. These papers shaped the course of 20th century mathematics in the most unimaginable way during his lifetime. The cold, damp English climate, wartime deprivation, and his strict adherence to vegetarian diet all conspired to make Ramanujan seriously ill. He was admitted to several sanatoriums, suffering from tuberculosis.
It's good for you, Mr. Ramanujan. Eat it all up.
Ramanujan, I just took a taxi cab, number 1729. Seems rather a dull number to me. What do you think?
1729. 729, 1000, and 1. It is the smallest number expressible. as a sum of two cubes in two different ways. Guess which?
Who? I?
1 cube plus 12 cube, 9 cube plus 10 cube. Very simple.
Is it indeed? Well, I suppose you wouldn't tell me the equivalent solutions to the fourth power?
I see no obvious example. But I suppose the first such number must be a very large one. I'm going back now. Home. With the same disease inside me.
You know you've been elected an FRS. You are a success. They want you here. You must fight your TB. You must.
Back in India, with scant concern for his serious illness, Ramanujan exhausted all his energies in formulating a new set of theta functions, which have now found applications in other areas of mathematics, today known as mock modular forms. It took mathematicians more than 80 years to unravel what Ramanujan meant by these enigmatic equations. A little over a year after returning to India, in the festering heat of summer, an ailing Ramanujan lapsed into coma and passed away soon after in this very house. He was young, only 32 years old.
Ramanujan recorded the discoveries that he made in the last year of his life on a collection of loosely ordered sheets of paper, which were dispatched to Hardy after Ramanujan's death. But several years later, this collection was misplaced, and so it came to be called the Lost Notebook. This collection was rediscovered only in 1976, when the mathematician George Andrews stumbled upon it in a box in the Wren Library of Trinity College, Cambridge. As we know, Ramanujan was a pure mathematician who was interested in numbers for their own intrinsic beauty. But, surprising as it may be, his work still has an impact on our daily lives. For example, Ramanujan's work tells us something about how to build transportation networks. Consider a road network between different cities or between different centers within a city. Google uses these networks to recommend alternate routes. As I'm sure you've experienced, these road networks are very prone to failures. Sometimes intersections become overly congested, or they're simply blocked off. So one wants a network with many alternate routes. Specifically, even when several nodes are congested, one would like to be able to have high connectivity between different locations in the city. Building a robust network then corresponds to constructing a graph with a large spectral gap. In 1988, three mathematicians, Lubotsky, Phillips, and Sarnak, constructed a class of graphs that achieved the maximum possible spectral gap for a given sparsity. These graphs came to be known as Ramanujan graphs because their construction used a 1916 conjecture of the Indian mathematician. This conjecture was later proved by the Belgian mathematician Pierre Deligne, who was awarded the Fields Medal, the most prestigious prize in mathematics. A second application of Ramanujan's work is important for modern web applications such as Facebook. In particular, Ramanujan-type graphs arise in the design of algorithms for detecting communities or groups of people with shared interests in such social networks. The study of such randomized algorithms is a part of the field of probability theory, which is my own domain of research. Thus, we see that Ramanujan's work from the early 1900s continues to have a profound impact on both fundamental and applied mathematical research to this day.
Today, nearly 100 years after his death, we find mathematics has slowly developed sophisticated tools, which are unraveling some of the secrets hidden behind his intuitive suppositions. Over the years, the mythical tree in Ramanujan's legendary garden has opened up new vistas of possibilities. New branches of mathematics have sprouted and proliferated and found application in varied fields of different sciences, implausible in his own times. His fertile mind envisioned a world where science and mathematics converge to uncover the fundamental principles governing our universe. This, then, is the legacy of a self-trained mathematician who straddled the world of numbers in early 20th century and continues to inspire generations of mathematicians even today.
Mathematics is like a beautiful jazz orchestra in which the creative melodies of different mathematicians harmoniously blend to form beautiful compositions. Ramanujan can be seen as one of the great conductors whose conjectures have spurred mathematical developments all over the world. Researchers continue to study properties of various mathematical constructs bearing his name. Thus, the legacy of Ramanujan is still very much felt to this day.